Today we are going to discuss about mean cost flow problem. The actual algorithm name is cycle cancellation algorithm. So actually in your syllabus it is cycle cancellation algorithm, which is the part of this network flow topic. You can consider it as the last algorithm. Okay. So actually we will be discussing cycle cancellation. Before that, we have to understand what is mean cost is cost flow problem. So earlier we know what is max flow, now it is mean cost flow. So let us understand what is mean cost flow. So in short, we will be calling it MCF, mean cost flow. Materials are not available so much, even in the book also. So it is a graph flow optimization problem. Mean cost flow problem is graph flow optimization problem. First thing, mean cost flow, graph flow optimization. Please, graph flow optimization problem. Second thing is, here the term, here the terms supply and demand shall be used for nodes in the network. Demand and supply, supply and demand. Third thing is, every edge has the capacity and cost, capacity and cost of shipping flow along the edges. Here the capacity should be always greater than 0. Positive capacity should be there. Fourth thing is, the communication flow, the communication of flow should happen from supply to demand. That means supply to the demand nodes, supply nodes, from supply nodes to demand nodes. and capacity along any given age should not exceed also. Okay, here are a few important points. Shall I rub it? Okay. Shall I go to the next? Now, difference between mean cost flow problem and maximum flow problem. Maximum flow problem already you know. Ford Fulkerson difference. First difference is that mean cost flow introduces supply and demand that are there in supply and demand in the notes. Second point, max flow problem. I mean, in this point itself, we can continue. Max flow, however, max flow problem however in max flow problem the supply and demand take place in terms of source and sink. That means source and sink concepts is there in max flow problem like Ford Fulkerson, but here it is supply and demand. Second point, very important point, the feasible solution sometimes might not be possible in case of mean cost flow problem. Similarity could be both the algorithms use graph network with capacities. Okay, shall I rub it? The mathematical prerequisite for mean cost flow problem. What are the mathematical notations and all you should know? First thing is that we have a graph here graph G, which consists with node and edges. Here node I should belong to N with, very importantly, with supply and demand. SI, supply and demand, will be referred as SI. Second point, if SI is greater than 0, we can refer that the node has a supply. That means if SI is positive, we will say that node has a supply of SI. On the contrary, if SI is less than 0, we refer node has a demand. Next point, every edge I comma j belong to E has capacity Q I comma j should be greater than 0, and also cost I comma j greater than equal to 0. Cost, important. This is an extra term that you are introducing in mean cost flow. Cost, that should be greater than or equal to 0. Okay. Shall I go to the next page? Okay. Next point, for flow to be successful, the following conditions should be satisfied. Condition number 1, Q of I comma j should be greater than equal to flow of I comma j should be greater than equal to 0. First condition. That means capacity should be greater than flow, and that should be positive also. First condition. Second condition, summation flow of I comma j minus summation flow k comma I should be equal to supply or demand, SI. Here j equal to I comma j belongs to E. Here k equal to k comma I belongs to. Now next, what is the meaning of this? Meaning is the sum of the outflow, the meaning of the above expression, this one, the sum of the outflows from node I minus the sum of the inflows to node I should be equal to supply or demand. This is the meaning of the above expression. Okay, important point. In case of mean cost flow problem, this supply can be greater than equal to 0, whereas in case of max flow problem, supply or demand is equal to 0. Equal to 0. Shall I go to the next? Now, converting mean cost, converting mean cost flow, which is in short MCF, as or to max. What is the algorithm for conversion? First point, make a new graph G dash, which is of new node N dash, new H E dash. How? Such that N dash equal to the current node union. You have to add on one source node and one sink node for source sink. Second point, S, the source that you have added, is equal to, that means one source and one sink you have to add to the mean cost flow graph. Then only you will go to max. You can apply directly max flow problem. You have added a source, so how the source will be S comma I belongs to V. How the sink will behave? Okay. T I comma E, sink node I belong to V. Here Si is greater than 0. Here I is belong to V. Si for sink node is less than 0. Next, capacity should be defined for the new edges in S and T as capacity of I comma J S of I S if J equal to T. Fourth point is G dash is an input to the max flow problem. After converting mean cost flow to max flow instance, we try to solve it. Okay. So one example I'll take, you will understand better. So you have to convert mean flow problem to max flow problem. Then only things will happen. But how mean flow problem will look like? Let us draw one network and understand. So let's assume this is 5, this is 2, this is -1, this is -3, -5, 3, and here in between the edges, the representation will change little bit compared to the max flow from 1 to, let's say, 2, 3, 2, 4, 3, 5, 1. So this entity, let's say this one, this 1, 2 that is in between this tuple, this is called cost and this is called capacity. Note that as negative input, those are demand node. And remaining all are, what is a supply node. Supply node, okay? Okay. Now you have to convert it. How to convert? You see the algorithm, all of you. Algorithm it says that you have to add a sink node and a source node and a sink node. So you have to add a source node here and a sink node here. So let's say this source node has been added. Let's call it S. Sink node, let's call it T. Now this source node you have to add to the starting node which is given for mean cost flow problem. Because this fellow is having 5, so the supply should be 5 here. And also you send it to the this node, supply should be 2. And you can send to this node also, supply should be 3, otherwise it can't get 3, it can't get 2, it can't get 5. For this demand node, what you have to do, you have to, because this is -1, this -1 cannot send anyone, so you have to forcefully have to add it with +1, you have to add it with +5, you have to add it plus. Now you have to redraw this algorithm. Write down, friends. Redraw the following figure so that you get below graph. How it will look like, students? S2, S, T, 5, 2, 3, 4. Here earlier, what was the, here I forgot 2, comma 4. This is 4, 5, 1. This you keep it as it is. -1, -5, 3. No. After getting this graph, apply any max flow algorithm such as Ford-Fulkerson or even Edmond curve also you can apply. Ford-Fulkerson and find the maximum flow. Okay, students. Now, while doing so, up to this much is clear. But in our syllabus, the topic is cycle cancellation algorithm. All of you have done this thing. Shall I go to the next? Like, but our topic is cycle cancellation algorithm. While doing that, you can have a cycle, negative cycle. So first of all, we have to understand what happens. Any doubts? What is negative cycle? What is negative cycle? You have to understand. First of all, what is cycle and how it is creating problem in the graph. A negative cycle in a weighted graph that side generate one attendance, this side also generate one attendance. Weighted graph is a cycle whose total weight is negative. Students, any algorithm you know that can find negative cycle, that can detect negative cycle? Any algorithm you know in a graph, weighted graph? Very good. I forgot your name. Name? Siddhant. Bellman-Ford algorithm. So you can write it down here. Bellman-Ford algorithm finds, or better term is detect, negative cycle in a graph. Why it is a problematic thing? Because if you trap in a negative cycle, that's all over. You cannot calculate the optimal path. Okay. So there are other algorithms also which may be in trap zone, which is called Dijkstra algorithm. That also suffers from negative cycle this thing. So this is just outside of the thing, so I'm just make it in bracket. Bellman-Ford is the algorithm which, now let us see. So one graph is given to you like this. 2, 1, 3. So this is 3, this is weight is 1, this is 2. The total weight is 3 plus 1 plus 2, which is 6. So no negative cycle here. Okay. But if I give you a graph like this, 1, 2, minus 6, 3. Total weight in this case, minus 6 plus 3 plus 2, which is minus 1. So it's negative. The negative cycle is this. Shall I go to the next? So in a larger graph, how things will look like, you may encounter with a negative cycle like this. Let's say this is 0th node, first node, second node, third node. So if you come in this zone, it is a cycle, and total is minus 6 plus 3, 2. So it's a negative cycle. So this negative cycle is totally, we have to avoid this. How to avoid, how Bellman would avoid this negative cycle? A technique called relaxation. Relaxation technique. What is the technique says? Let's say we have one path from A to B, another path from B to C, another path from A to C. So let's say this is 6, this is 2, and this is 5. So distance between A, B plus distance between D, B, C is equal to 6 plus 2, which is 8. If it, so let's say first attempt it has find this path, but then if suddenly, let's say there are other nodes also, like this kind of nodes are available, if it by any chance encounters with other nodes with other possibility, but suddenly it encounters this path, which is nothing but distance of AC, which is equal to 5, then what it will do, it will relax this path, it will ignore this path, it will accept this path. Is much more. So this 5 is less than 8. Whichever is less than that path it will choose. This process is called relaxation technique. By this technique, Bellman could detect cycle. Okay, friends, up to this much. Next class, I'll try for how it can be negative cycle we can encounter in a graph, and then how to sort it out. That will be your negative cancellation, cycle cancellation. The time. 33. Okay. Do you have covered? I have covered Jarvis March. No, no. Jarvis March algorithm from Jarvis covered. No, no. So we have